Close your eyes and picture Mars the way we have been shown it for decades. Gleaming glass domes catching a butterscotch sunset, green shoots rising neatly from red soil inside a warm, humming greenhouse, children running between habitats under a pink sky. It is a beautiful picture. It is also, and I say this as someone who has spent decades studying exactly what that planet is actually made of, almost nothing like the truth. I want to walk you through what Mars actually is, layer by layer, the way an engineer would, rather than the way a poster artist would. And I think once you see it clearly, you will understand why so many serious scientists now use a very specific, very careful word when they talk about permanent settlement there. Not difficult, not expensive, impossible, at least with anything resembling the physics and biology we currently understand. Today, we are going to find out why. And if you want to keep exploring the honest, unfiltered reality behind humanity's biggest dreams with me, make sure you are subscribed, because by the end of this journey, that pink sunset may look very different to you. Let us begin with the very first thing you would lose the moment you left Earth behind. Something so constant, so automatic, that almost nobody ever consciously notices it protecting them at all. Picture standing outside during a violent hailstorm, completely shielded beneath an enormous invisible umbrella, one so effective you never feel a single strike, never even think to look up and check if it is still raining. That invisible umbrella is Earth's magnetic field, generated by a churning ocean of molten iron deep within our planet's core, deflecting the overwhelming majority of the radiation constantly raining down from the sun and from the wreckage of distant, long-dead stars scattered across our galaxy. Mars lost its own version of that umbrella roughly 4 billion years ago, when its small, quickly cooling core stopped generating one at all. Stand on its surface today, and that umbrella is simply gone, folded up and put away forever. NASA's own instruments carried aboard the Curiosity rover have measured exactly what this means in practice. A single round-trip mission, transit time included, would expose an astronaut to a radiation dose meaningfully beyond every career safety limit we currently use, dramatically raising lifetime cancer risk, with real documented concerns about long-term effects on the brain itself. This is not a problem you solve with a better jacket. Meaningful protection requires walls of water, lead, or packed soil meters thick, which means anything resembling permanent life on Mars likely means permanent life underground, buried away from the very sky that was supposed to be the whole point of going there. There is a second, sharper edge to this same danger, one that arrives not as a steady drizzle, but as a sudden storm. The sun occasionally releases massive bursts of high-energy particles called solar particle events, capable of spiking radiation levels to lethal doses within hours for anyone caught unprotected. Picture a hiker exposed on an open ridge, watching a lightning storm build on the horizon with nowhere to take shelter for miles. On Earth, our magnetic field and atmosphere absorb the vast majority of this before it ever reaches us. On Mars, with no equivalent protection, a large solar event could deliver a dangerous or fatal dose to anyone caught outside a heavily shielded shelter, turning even routine surface work into a gamble against an unpredictable sky. Now let us go even further to something almost nobody puts in the concept art at all: the soil itself. Picture a farmer, generations deep in tending the same land, only to discover one day that the soil beneath their feet has been quietly poisoned the entire time, contaminated with something toxic to every living thing they hope to grow in it. Martian regolith contains significant concentrations of a chemical compound called perchlorate, found not in one isolated patch, but seemingly across much of the planet's entire surface, known to interfere directly with human thyroid function. Grow food in that soil without extensive processing first, and you risk slowly poisoning the very colonists that soil was meant to feed. This is not a hurdle. It is closer to discovering that the ground itself, the most basic requirement of agriculture anywhere in human history, has to be entirely engineered around before it can be trusted at all. Let us talk about the air, or rather, the almost complete absence of it. Picture a deep-sea diving bell, its entire design built around holding back the crushing pressure of the ocean from the outside in. Now imagine that same bell turned completely inside out, its walls now needed to hold pressure in against an outside world with almost none at all. Mars's atmosphere sits at less than 1%, the thickness of our own, composed overwhelmingly of carbon dioxide, offering no meaningful pressure and no breathable air whatsoever. Or step outside a habitat unprotected, even briefly, and you would lose consciousness within seconds, not primarily from lack of oxygen, but because your own bodily fluids would begin to vaporize in the near vacuum pressing in around you. There is no acclimating to this the way mountain climbers slowly adjust to thin air on Earth. It is a permanent, absolute boundary, one single equipment failure away from catastrophe for every single day of a colonist's entire life. There's a fifth danger, one that arrives without warning and can last for weeks at a time. Picture a lighthouse keeper watching a fog roll in from the sea, except this fog does not lift after a day or two. It swallows the entire coastline and stays there, thick and unmoving, for a month. Mars occasionally experiences global dust storms, events large enough to envelop the entire planet at once, as happened in 2018, when a storm blocked so much sunlight that it permanently silenced NASA's solar-powered Opportunity rover, ending a mission that had lasted nearly 15 years in a matter of weeks. Any colony depending on solar power would face the exact same vulnerability, its primary energy source vanishing behind a wall of dust for an unpredictable stretch of time, with fine particles infiltrating seals, equipment, and habitats no matter how carefully engineered they are. And even the temperature refuses to cooperate. Because the atmosphere is too thin to hold on to heat, Mars can swing more than 100 degrees Fahrenheit between day and night at the very same location. A thermal whiplash that every seal, every joint, every piece of equipment would need to survive over and over, for years without a single failure. Radiation with no umbrella left to block it. Soil that must be treated like a poison before it can feed anyone. An atmosphere that offers no pressure and no air at all. A climate that swings wildly within a single day. Each one of these, on its own, is the kind of problem engineers are genuinely good at solving. Underground shelters can handle radiation. Processing systems can filter perchlorates. Pressurized habitats can hold back the vacuum. But here's the question I want you to sit with as we move into the second half of this journey. What happens when every single one of these problems has to be solved simultaneously, permanently, without a single failure for an entire population across multiple generations on a planet that offers no natural margin for error anywhere at all? That is exactly where we are headed next. Stay with me. We walk through radiation with no umbrella left to block it, soil that must be treated like a poison, an atmosphere offering no breathable air at all, and a climate that swings wildly within a single day. But I left you with the hardest question of this entire journey. What happens when every one of these problems has to be solved simultaneously, permanently, for generations, with zero margin for error? Let me start with something that rarely makes it into the conversation at all, because it sits beneath even biology itself, in the most basic physical property of the planet: gravity. Mars pulls at just 38% the strength Earth does. We know from decades of research aboard the International Space Station that the human body evolved entirely around Earth's specific gravitational pull, and that removing it entirely causes measurable bone density loss, muscle atrophy, and changes to the eyes themselves. What we genuinely do not know, and I want to be honest with you about how big a gap this actually is whether 38% gravity meaningfully slows these effects, or whether it simply delays the exact same outcome by a few extra years. Picture a plant bred over countless generations to grow perfectly upright in the specific gravity found on one particular hillside. Move it to a hillside with different soil, different rainfall, different sunlight, and even if every other condition is carefully matched, its roots, its stem, its entire structure may simply never develop the way they were meant to. No human being has ever lived in partial gravity for more than a few days during brief lunar missions decades ago. Mars would effectively make every single settler part of an uncontrolled multi-generational experiment on human physiology, with no way to know the true outcome until people have already spent years or entire lifetimes living inside it. This leads directly to the single most consequential unknown in this entire conversation, one I think deserves far more attention than it usually receives. Reproduction. No controlled study has ever tested whether human conception, pregnancy, and childbirth can proceed safely in partial gravity at all. Limited research on mice in simulated microgravity aboard the space station has shown developmental complications, though results remain mixed and the number of animals studied remains small. This means the single most basic requirement for any colony to ever become genuinely self-sustaining, rather than permanently dependent on shipments from Earth, remains a complete, unanswered question, one that cannot ethically be tested directly until someone is already willing to risk the outcome themselves. Now let me show you something that looks on the surface like the most solvable problem of all, and turns out to be far more fragile than it appears. Growing food. Picture an elaborate glass terrarium, sealed shut, containing everything a small ecosystem needs to sustain itself indefinitely. Water, soil, light, air, all perfectly balanced. Terrariums like this look stable for a while. But biologists who study them know something uncomfortable, that even small, self-contained ecosystems are notoriously difficult to keep in balance over long periods, prone to sudden cascading collapse if even one single variable drifts even slightly out of range. A Mars colony's food system would be exactly this kind of sealed terrarium, except failure would not simply mean dead houseplants. It would mean starvation for everyone depending on it, with no possibility of a fast resupply from Earth, since even under ideal planetary alignment, sending help takes 6 to 9 months just for transit, plus additional time to prepare and launch in the first place. A single equipment failure, a single unexpected contamination, a single miscalculation in a sealed agricultural system could threaten an entire population's survival within weeks, with no realistic outside intervention possible before the outcome had already been decided. And underneath all of this sits something that cannot be engineered at all, something entirely human. Isolation. Real Mars missions, even under the most optimistic timelines, commit crews to 2 to 3 years away from Earth at absolute minimum. NASA's own simulated isolation studies, conducted in places like remote volcanic terrain in Hawaii, have documented genuine psychological strain under conditions far milder than an actual Mars mission would involve. Interpersonal conflict, disrupted sleep, and a slow erosion of morale that grows heavier the longer confinement continues, with communication delays back to Earth stretching up to 24 minutes each way, removing even the comfort of a real-time conversation with anyone who has ever actually experienced home. There is one more layer to this, one that determines whether a colony is truly a settlement or simply a very expensive, very remote outpost: self-sufficiency. Picture a newborn colony, still entirely dependent on packages arriving from far away, the way an infant depends entirely on being fed, unable yet to produce anything at all on its own. Early Mars settlements would depend heavily on shipments from Earth for critical components, specialized electronics, medicine, precision manufactured parts that cannot easily be produced locally with any technology likely to exist in the coming decades. NASA has made real, genuine progress here, its Perseverance rover successfully producing small amounts of oxygen directly from the Martian atmosphere in 2021 through an instrument called MOXIE. But scaling that single successful experiment up into a population capable of producing its own food, its own medicine, its own replacement parts, entirely without help, remains a task that would likely take decades of patient infrastructure development, even under the most optimistic possible timeline. And when something does go wrong, there is no fast answer waiting nearby. On Earth, even in the most remote locations, help typically arrives within hours or days. On Mars, depending on the position of the 2 planets in their orbits, sending emergency supplies or personnel could take 6 to 9 months just in transit, plus additional time to prepare the mission in the first place. Picture a patient in a remote clinic, discovering that the nearest specialist capable of treating them lives on the other side of an ocean, with no ships currently sailing. That is the reality any serious medical or structural emergency on Mars would face, a colony forced to be almost entirely self-sufficient in crisis response, simply because there is no version of a fast rescue that the laws of orbital mechanics will ever permit. Here's what I want you to notice now that we have walked through all of this together. Radiation, toxic soil, no breathable air, wild temperature swings, unknown effects of partial gravity, an unanswered question about reproduction itself, a food system as fragile as a sealed terrarium, profound, sustained isolation, Individually, brilliant engineers have made real, genuine progress on nearly every one of these. NASA's Perseverance rover has already demonstrated producing small amounts of oxygen directly from the Martian atmosphere. But solving each problem individually is not the same as solving all of them simultaneously, permanently without a single failure for a population large enough and stable enough to survive across multiple generations without depending indefinitely on a planet 140 million miles away. This is why so many serious researchers now draw a sharp, deliberate line between visiting Mars and settling it. A crewed visit, landing, conducting research, and returning home sits within reach of the coming decades and represents one of the most exciting achievements our species could ever attempt. A genuine, self-sustaining civilization there. One where people are born, live full lives, and raise the next generation without Earth's help may require solving problems that remain, as far as our current science can tell, not simply difficult, but structurally, physically unresolved. So where does this leave us at the end of our journey together? Perhaps the honest answer is not a flat, permanent no. Science has surprised us before, and I would never claim to know exactly what tomorrow's breakthroughs might make possible. But right now, today, with the physics and biology we actually understand, living permanently on Mars is not simply an engineering challenge waiting for enough funding and enough courage. It may be asking an entire planet's chemistry, gravity, and biology to bend into a shape it was never built to hold, all at once, with absolutely no room left over for a single mistake. Exploring the honest gap between our dreams and our actual physics is exactly why I do this work, and exactly why I wanted to walk through this particular journey with you. If this changed the way you look at that pink Martian sunset in the concept art, then make sure you are subscribed so we can keep exploring these questions together. Tell me in the comments, honestly, knowing everything we just walked through, do you still believe humanity will call Mars home one day? Until next time, keep looking up and keep asking what a dream actually costs before you chase it.